Let's look at this problem you just finished on the bottom of page 15-7. In this case, we have 1 mole of NO2 gas reacting with NO gas to make N2O and O2. And we know that the K sub C is 0.914. So if we look at the second equation, we try and figure out how it's related to the first one. And it's been reversed and multiplied by 2. So to get the new K value, we take the reciprocal, 1 over my original K1, and then we square it. So it's 1 divided by 0.914, the quantity squared, and we get 1.20, and that's our new K value. So you should be able to manipulate these equations around as you multiply by coefficients, add equations, or reverse the equations. And that'll be something we're going to play with over the next 3 chapters. Now, sometimes we work with reactions that contain all gases. And if they have all gases, instead of looking at the molar concentration, we can actually use the partial pressures of the gases. We remember from intro chemistry or Chem 111 that the ideal gas law, PV equals nRT. We can rearrange that P is equal to nRT over V, or N over V times RT. And N is moles, V is the volume in liters, so it's the molarity times the gas constant times the temperature. Since we're looking at this relationship, we could write then the pressure is equal to the molarity times some constant, because R is the gas constant, and if we hold the temperature constant for a given experiment, then we have a constant temperature, which multiplied by a constant becomes a constant. So we can now use this idea, and we can write mass action expressions using pressures instead of using molar concentrations. In order for this to work, we have to have all gases in the equation. So let's look at this example. Nitrogen gas reacts with 3 hydrogen gas to make 2 ammonia gas. We can write a new equilibrium constant, and I call this one K sub P because we're using pressure instead of concentration. So that's equal to the pressure of the ammonia gas, and we square that just like before because of the 2 and the coefficient in the balanced equation, divided by the pressure of nitrogen gas to the first power, because I have a 1 here, times the pressure of the hydrogen gas cubed. Now you take a minute and go ahead and write the equilibrium law for this reaction using partial pressures. Just pause the video while you're working the problem and then restart it. Did you get what I did? K sub P is equal to the pressure of hydrogen iodide, the quantity squared, divided by the pressure of hydrogen times the pressure of the iodine. So it's very similar to what we did previously. Now, K sub P, the pressure constant, and K sub C are actually related to each other. And sometimes they are numerically the same, other times they'll be different. And we can look at the mathematical relationship that the 2 constants have to each other. We can actually calculate K sub P from K sub C for reactions where they're numerically different, or the same really, using this relationship. K sub P is equal to K sub C times RT raised to the delta N sub G power. R is the gas constant, T is the Kelvin temperature. K sub C has units of moles per liter usually, or liters per mole, or something in there. A lot of times they cancel. But the delta N sub G, which is the exponent, is the interesting part. This is the change in the number of moles of gas. And we think of it as number of moles of gas in the products minus the number of moles of gas in the reactants. It's always products minus reactants for us in chemistry. And we can calculate this delta N sub G by looking at the coefficients in the balanced equation. So let's look at this example. At 500 degrees Celsius, the reaction below has a K sub C value of 6.0 times 10 to the negative second. What is the value of K sub P? Well, we know K sub P is equal to K sub C times RT to the delta N sub G. So we'll start off, we know K sub C, let's find delta N sub G. I have 2 moles of gas on the product side, and I have 1 mole of nitrogen and 3 moles of hydrogen, so I have 4 moles of gas on the reactant side. So my delta N sub G is equal to 2 moles minus 4 moles is negative 2. Now, the negative sign is important in this because it depends which way you're going. So we make sure we put that negative 2 in the exponent. So we can go ahead and plug this in now. K sub P, what I'm trying to calculate, is equal to K sub C, 6.0 times 10 to the negative second, times the quantity, R, the gas constant, 0.0821 liter atmosphere per mole Kelvin, times the Kelvin temperature, 773 Kelvin. I had 500 degrees Celsius stopping with my last significant figure in the ones place. So this whole quantity is raised to the negative 2. Now remember, when we have a negative exponent, that's like taking the reciprocal. So I can think of it as this number in the bottom of a fraction, and that number is squared. So I went ahead and just multiplied across. K sub P is equal to 6.0 times 10 to the negative second. This whole quantity comes out to be 63.5 to the negative 2. So I like to rearrange it this way. 6.0 times 10 to the negative second divided by 63.5 squared. The negative 2 becomes a positive 2 in the bottom of the fraction. Now I can plug that in. 1.5 times 10 to the negative fifth is equal to K sub P. And it's always hard trying to figure out if you have a reasonable answer. Since K sub C was reasonably small, we'd expect K sub P to be fairly small as well. So now go ahead and try this next one. Go ahead and stop this video. I will show the solution on the next video.